In this lecture, we want to do these calculations for silicon lattice. Self-consistent field calculation, find appropriate values for wave function cutoff energy and baryon zone sampling K point. Also, we want to do variable cell relaxation for silicon. As you can see, this is the silicon crystal lattice that is FCC type. This is silicon crystal lattice. It has 3 unit cell vectors. You can see it. Also, we can see the input file here. iBrave equals 2, which means FCC lattice. The side of the cube is 10.2625 Bohr. That defines as Ceylon 1. We note that our pseudo potential is ultrasoft type. In this case, cutoff energy for density usually is 8 times cutoff energy for the wave function. Also, you can see atomic position here in Cartesian coordinates in units of lattice parameters. As we said before, we can use PWGUI interface to create an input file, or we can write it manually. I choose File, New. We specify the type of calculation, that is SCF self-consistent field. The restart mode is from scratch. The prefix is SI, the abbreviation of silicon. The directory for input-output file and the location of pseudo potential should be specified here. I created a silicon folder here. In the System tab, we choose face-centered cubic FCC lattice. That means iBrave equals 2. As we said before, we can specify the lattice by ABC parameters or sell them. In this example, to be different from the previous example, I choose sell them. From the silicon lattice information from books and journals, we know that the side of the cube is 10.2625 and the unit is Bohr. We write its value here. Also, from quantum physics, we know that the number of atoms in the unit cell is 2. In the unit cell, only there are silicon atoms. Therefore, the number of atoms type is 1. We specify 60 Rydberg for wave function energy cutoff and 720 Rydberg for density cutoff. These values are optimum values for the wave function energy cutoff and cutoff energy for density. We go to the optional variables section. We choose PBE for input DFT. We know from pseudo potential file content that exchange correlation type is PBE. Then we specify a smearing for occupation because our calculation is self-consistent field, and choose the type of function to be Gaussian. And the dgauss is 10 to the power of 4. Then we go to electrons tab. We specify the convergence threshold for self-consistent field to be 10 to the power of -8. Also, the mixing beta is 0.7. Then we go to lattice and atoms tab. In the atomic species, we choose atomic label to be C, and atomic mass is 28.0 0.0855, and then we should give the root of pseudo potential file that we got it from the Quantum Espresso web page previously. Atomic position are in the unit of ALAT, the length of unit of cell 1, x coordinate 0, y coordinate 0, z coordinate 0 for first atom, and 0.25, 0.25, and 0.25 for second atom. We obtain these information from material science. To obtain these informations, you can refer to Quantum Transport book, and in page 116, you can see this atomic position information in this book. Also, we define the K point to be 4 times 4 times 1. This is its optimum value that we will obtain further. Then we should save the input file. Before run, it is useful to take a look at the input file. You can see it here. And then we can run it. The run is over. We can see the output file here. We can see the total energy here, and also the Fermi level energy. These information can be obtained from output file. Now we want to do the second and third calculation. One of the important issues is to find appropriate value for energy cutoff and also for K point. As we said before, energy cutoff for wave function determines the size of the plane wave basis set to expand the wave functions. As the energy cutoff increases, the total energy decreases until convergence occurs. That energy will be its appropriate value. To find it, we should change the value of energy cutoff in the input file and see the output. To do this, we create a folder. In this folder, there are 32 input files. In this input file, the energy cutoff is changed from 4 Rydberg to 100 Rydberg. For example, this file, you can see energy cutoff is 18. In this file, energy cutoff is 60. And in this file, energy cutoff is 100. We should run self-consistent field calculation for each input file and then collect the total energy from output files. Another point is that before we run the program, we can see the figure of lattice. by selecting View Structure with X-Crysting. You can see this is the figure of silicon lattice that is face-center cubic. You can see this figure. This is face-centered cubic lattice. Then we should run the code. As I said before, we should run self-consistent field for each input file. In this case, we have 32 input files. For example, in this output file, we can see the total energy here, and we should do it for each of 32 files that we created in this folder. I do it for all of these files, and I collect this data in a file, this file here. In this file, there are two columns. The first column contains energy cutoff, and the second column contains the total energy that extracted from output file. Plot it. I open terminal environment and use GNU plot, and then command plot my name of created file. You can see the figure here. From the figure, we can find that the total energy reached convergence at the energy of 16, and the 16 Rydberg is high enough for our calculations. Then we should find the appropriate value for K point. The method is similar. To reach convergence with respect to K point, we should change the K points and then see the total energy. You can see that I created 21 files here. We choose K points from 1 times 1 times to 10 times 10 times. For example, this file, the K point is 2 times 2 times 2. This file, K point is 7 times 7 times 7. The K point started from 1 times 1 times 1 to 10 times 10 times 10. And after that, we should run self-consistent field for each of these input files. You can see in this case, K point is 9 times 9 times 9. And then we run the file. All of the output file are created. I collect the total energy from these files. You can see in this file there are two columns. The first column contains K point and the second column contains total energy. The name of file with lines. You can see this, and from the figure we can find that the total energy reaches convergence at the K point of 4 times 4 times 4. I brings these two figures here, convergence for cutoff energy and convergence for K points. And the last calculation that I want to explain in this section is VC relax calculation or variable cell relax calculation. As we said before, one of the important calculations is variable cell relax calculation or VC relax calculation. This is VC relax input file, in this case cell lattice parameters and atomic coordinates may be changed by relaxation. The VC relax code runs several self-consistent fields to find the minimum of system total energy according to various lattice vectors and various atomic coordinates. We do it by PWGUI graphical interface. We choose variable cell relax calculation, restart mode from scratch. We choose the directory for input output and also pseudo potential. Then we should define the threshold for forced convergence here, 10 to the power of minus 5. The system section is unchanged. Also the electron section is unchanged. Then in the ion tab we specify BFGS here for ionic dynamic. As we said, the variable cell section, the variable cell tab, is used only if the calculation is variable cell relax or VC relax. The default type of dynamic cell is BFGS. Press convergence threshold. This parameter is convergence threshold and the pressure for variable cell relaxation is default value is 0.5. The lattice section is unchanged and also the atomic positions. K point value is 4 times 4 times 4. And then it is ready to run. After some time, the run is over. We can see the output file here. If we see the cell parameters at the end of output files, you can see that ALAT is 10.25. The final cell is printed after the last cell parameter card. Each row defines a vector. Also, each vector is multiplied by ALAT. We should find the correct value for ALAT. The output file gives us 10.25 Bohr for ALAT. But we can see in the vectors, you can see that FCC vectors are changed. I bring these results here. You can see these results here. The code gives us this value for ALAT 10.25. We want to change ALAT so that the lattice remains FCC. The output file gives us 10.25, but in the vectors you can see that FCC vectors are changed. It changed from 0.5 or half to 0.504. We can modify the ALAT value such that the lattice remains FCC by multiplying this ALAT to 0.505 divided by half. And this value is the corrected value for ALAT, and we will use it in our next calculations.